Welcome everyone to the second YouTube Global R&D meeting of 2026. I'm Björn. I'm leading the governance team here at DFINITY, and I'm your host today. So, through a couple of last months, we have seen great progress across several ICP projects, and we'll walk you through some highlights today. We'll start with an update on ecosystem metrics, followed by features updates, in particular chain key performance improvements, news on secure SEV subnets, and also additional options for critical proposals for SNS DAOs. We will conclude with two demos, the first one being ckDOGE, and the second one being a community demo from the Liquidium team. With that, I hand over to Kyle for metrics.
Thanks, Bjorn. Appreciate it. And congrats to the Liquidium team on a successful launch yesterday. Really good stuff, and excited to see the demo. If we jump to the first slide, there we go. So I want to give a caffeine-specific update on some of the network metrics. First, I want to start with canister growth, because I think this is one of the easiest ways to measure caffeine's effect on the network. So what you see here is since July 15th, basically what I used as the starting point for caffeine's go live, the number of gross new canisters. So this is the difference between new canisters added to the network minus any canisters that were deleted off the network. And you can see, I mean, just really through the summer and fall, kind of a pretty steady baseline of, I don't know, what is that, like 400 a day, 300 a day, maybe. You start to see in October start to increase, and then November and December is where we really started taking off. Just to kind of give you some numbers to that, in November, we saw almost 14,000 new canisters. By December, that was 20,000. January, 56,000, let's say. In February, we're already up to 58,000. We'll almost certainly eclipse 60,000 for this month. So we're starting to see what you might call the hockey stick growth, which is awesome to see. But more importantly to me, you do see some spikes there in January and February. But more important to me is that baseline, that maybe what you might call like the 30-day moving average, has really showing a nice growth trend there. If I move on to the next slide, you can see different way to measure it. Canister state, you don't see that hockey growth, but you do see nice steady growth. And I'm going to get into kind of the difference between the two in a bit here. But just wanted to point out that, we back in July, we were right around 8 terabytes of data on the network. And now we've eclipsed 12 terabytes. So easy math says that's a 50% increase since then. If we go to the next slide, I want to talk really quickly about the difference between like a leading and a trailing indicator. So if you imagine a caffeine user, so a dev who's building on caffeine, if you imagine their journey, first they'll start with the project in draft mode. In draft mode, that's a new canister. A canister that only lives temporarily until after some point there's a garbage collection on it. But they work in draft mode for a while, then they push it live. Now we have a new canister that gets launched. However, that's only when their work starts, right? Once you have a project online, now you've got to market it. Now you've got to get your users on it. Once you start doing that, those new users may be using internet identity. A lot of apps on caffeine apps are using internet identity. So you should start to see internet identity logins start to grow. You should start seeing that canister state start to grow as users are creating more and more data on chain. And then obviously that should report back as cycle burn. But there is a lag in those three: canister state, internet identities, and cycle burn. From when the project starts, there's a lag before you see that project reflected in the data. And so what I'm saying here is I've shown you canister growth as a leading indicator. I expect that next month I come back, or whenever I'm invited back, I'll come back and report on some of these trailing indicators, and hopefully we start seeing that hockey stick growth in those as well. And I know my time's almost up, so we'll go to the last slide just real quickly. I've gotten a lot of questions about ckBTC in the last 2 months. I just wanted to give a quick update just to show ckBTC supply. So this is the past 12 months. So you can see this time last year, we had about 20 or 200 Bitcoin worth of ckBTC minted. That's now up to 360. So nice growth there. And obviously with projects like Liquidium launching, hopefully we start to see some effects of that in the ckBTC supply as well. So with that, I'll end my time. Feel free to ask any questions in the comments.
Thank you very much, Kyle. And it's great to see how caffeine is affecting the ICP usage quite heavily already for the last month. Thanks. Good. Now, next one would be chain key performance improvements. And I hand over to Leo.
Thank you. Yeah, so I'm Leo from the consensus team here at DFINITY. So what are these performance improvements about? So as you might know, the Internet Computer Protocol currently implements a threshold signing service for 4 different schemes. And specifically, it offers ECDSA. We have 2 different Schnorr schemes. And as of last year, also wet keys. And in essence, this service allows canisters to obtain their own public-private key pairs, where the private key is securely secret shared among all nodes of a subnet, such that it's never fully revealed to anyone. But at the same time, the public key can be made known to anyone and could then represent a wallet address of the canister, for instance, which would allow it to hold different kinds of tokens, for example. And so even if nobody knows the private key directly, the canister can still use it to generate signatures. So for instance, the canister could sign a transaction for a different blockchain network to transfer some tokens, for example. Now, on the next slide, you can see that until recently, the signature throughput, so how many signatures this service can create per second, was still a bit limited. So at the time we saw subnets reaching their limit at around 0.5 signatures per second for ECDSA, 1.1 per second for Schnorr, and 5 for wet keys. And so while it's important to say that these numbers are actually still sufficient for the usage that we see today, they do make implementing some specific use cases a bit more difficult. And that especially applies to certain DeFi applications where activity often occurs in bursts. So sometimes single transactions may even result in many signature requests. So one example could be a single Bitcoin transaction that may involve signing multiple inputs, for example. And so that's why on the next slide, over the last couple of months, DFINITY proposed and implemented many different changes across multiple layers of the IC to improve the signature throughput for both sustained load and also higher load spikes. And so some of these changes, they're listed right here. So for instance, in the networking layer, we were able to reduce the memory usage under high load, as well as the overhead of errors and asynchronous primitives. We also managed to conserve a lot of bandwidth by replacing some very large payload fields with tiny hashes. Then moving on, we also managed to improve the performance of the crypto component by, among other things, moving a previously file-backed secret key store into main memory. And we also streamlined the interface between the crypto component and the replica to reduce inter-process communication and avoid the need for cloning data in many places. And on top of that, we also improved the performance of many cryptographic primitives that are relevant for threshold signing. And then finally, in the consensus layer, we improved the performance of this signing service by enabling multi-threading for cryptographic operations. We also reduced the impact in general of high signature load on a subnet by moving expensive operations out of the critical consensus paths. And then lastly, we started storing pre-signature artifacts in the subnet's replicated state, which I want to go into a bit more detail on the next slide. So serving ECDSA or threshold Schnorr signature requests, they consume one of these pre-signature artifacts. And you should know that these pre-signatures, they're actually quite large and also very expensive to compute. So in reality, they are the main bottleneck of the signing service when it comes to performance. But the good news is that we can pre-compute these pre-signature artifacts in advance and then cache them until a request comes in, at which point one of the pre-signatures will be consumed. But now the problem is that up until recently, we could only create up to 5 of these pre-signatures in advance. And that is because they were stored as part of consensus payloads, where the space is naturally very limited. So that means that effectively we could only really serve up to 5 requests in quick succession before we needed to wait a while until more pre-signatures are generated, which will take some time. And yeah, so that is, of course, pretty bad for applications that want to request many signatures at once. So in particular, more than 5. Yeah, so that's why on the next slide, you can see that today we instead deliver these pre-signatures to the execution layer, where they are stored in the subnet's replicated state. And yeah, because the space there is much less limited, this allows us in turn to store significantly more pre-signatures in advance, to the order of thousands even. And because we store many more pre-signatures, we can also serve more signature requests in parallel before we need to wait until more pre-signatures are generated. And that is, of course, very beneficial for handling spikes of high load. Yeah, and additionally, we can also now make use of times with lower load by using that time to generate more pre-signatures to then be better prepared for when there is actual load. Right. Yeah, so thanks to all of these changes, on the next slide, I'm happy to announce that all of these improvements combined increased the sustained throughput limit of a specialized signing subnet by a factor of about 10x. So compared to before, the subnet limits for a sustained, so an ongoing stream of signature requests, are now at around 5 signatures per second for ECDSA, 18 for Schnorr, and around 60 for keys. And yeah, so on top of that, thanks to the fact that we can now store significantly more pre-signature artifacts for ECDSA and Schnorr, the subnets can observe an even higher maximum throughput in excess of 100 signatures per second during spikes of high load. That, of course, only as long as there are still enough pre-signatures available that we can consume. Yeah, so here in the graphic on the right, you can see that the leftmost bar of each scheme is the old limit before the changes. Then the next bars to the right are the new limits for the sustained throughput, so roughly a 10x improvement. And then for ECDSA and Schnorr, there is a third bar for the maximum throughput during load spikes, which is around 100 signatures per second, which is the rate at which we are consuming the pre-signatures that we stored in the replicate state. Yeah, there's no third bar for keys because that scheme doesn't use pre-signatures. Yeah, so here I also want to mention that the maximum throughput limit that can be reached is by a subnet that was specifically configured for a high signature load, and that limit applies per subnet. So as usual with the IC, we can additionally scale horizontally by adding more chain key signing subnets, which then, of course, multiplies the throughput, the maximum throughput, by the number of subnets. Yeah. So on the last slide, you can see that these changes are already live on mainnet today. And 2 weeks ago, the community also adopted a proposal that slightly increases the parameters of the production subnet from previously 5 pre-signatures to, for now, 100. And this in turn allows the subnet to also serve more signature requests in parallel. So these numbers on the slide that you see now, they are the maximum throughput achieved by some performance test against mainnet after the parameter increase. And so important to say that was just a conservative parameter increase, and we will continue to monitor the usage and the performance of the signing service as demand further increases. And then if necessary, DFINITY will propose further parameter increases that would get the subnet even closer to the maximum throughput limits that I showed on the previous slide. That's all I have. In the end, I would also like to advertise our forum post and ask that if you have an application or use case in mind that would require a higher signature throughput or more pre-signatures than currently configured, please join the discussion there so that it can be taken into account for any future parameter increases. Thank you.
Yeah, thank you, Leo. I think these are pretty impressive performance improvements, and also linking to the metrics update. I think it's pretty crucial on that to work on that front, because that allows us to grow further the ecosystem and run further projects. Very cool. Thank you. Good. So now let's go to more secure SEV subnets. Over to you, Rudy.
Yes. Thanks, Björn. Hi, everyone. My name is Rüdiger from the Node team, and we have been all together on the journey to bring trusted execution environments to the internet computer. We have updated you along the way, and today it is yet another of those updates. So as you can see, we have the first subnet, which consists only of SEV-enabled nodes. So actually at the beginning of the year, the node providers put in some effort and redeployed their nodes, and we have now 30, I think even might be more than 30 SEV-enabled nodes on the IC, and 7 of them are part for more than a week now of the newly created SEV subnet. And I tried to capture this here with the finalization rate. The subnet has been chugging along quite well. It doesn't have any real load, so anything else would not be that good. But also it underwent already 2 upgrades without any issues. This is what I highlighted in the picture there. Next slide, please. And so last time when we presented something about the SEV, it was all about disk encryption and upgrades, which was crucial for having a single SEV-enabled node. And the big missing piece back then was subnet recovery. So what do we do if things go wrong and we need to recover a subnet? David, after me, will talk in more detail about it. But what I wanted to highlight is that we actually published an article on the Learn Hub, which covers all these topics. It covers the disk encryption, the upgrades. It gives you a primer on what trusted execution brings and how we make use of it on the IC. So I highly recommend to check this out. Just check the Learn Hub of the Internet Computer. And then next slide, please. And let's say the trusted execution journey is not completely done yet. On the one hand, we still have to put in some work to do attestation within the IC and also allow users to attest that machines are indeed running in a trusted execution environment. Until now, this can just be done by the metrics, so the observability cluster and the registry. And then the second part is also, I talked about the SEV subnet, which currently doesn't really have any load. So later this week, we'll send out a proposal to authorize a node team principal to install some canisters on this subnet to test it with different loads. And finally, as you can imagine, it's like this 80-20. There's a lot of smaller improvements and fixes, also like experience that we get from actually running it in prod. So we have to tie up some loose ends. And with that, I'm at the end of my part, and David will tell you more about the recovery.
Thank you. I'm David from the Node team, and I like to talk about the recovery process of SEV SMP-enabled nodes. But before I start, let me recommend to you the Global R&D from November, where I already gave an introduction about SEV SMP and its use on the internet computer. Or alternatively, I recommend the article on the Learn Hub that Rüdiger already mentioned, which contains a lot more details about the entire work. And of course, if you have questions, please ask them on the forum and we'll make sure to answer them. Now, on to recovery. Recovery is necessary if the network stops working for some unforeseen reason. Our release testing is continuously improving. For example, in 2025, we didn't have to do any emergency recoveries at all. But bugs can never be fully excluded, so we need to prepare our nodes for emergencies. I like to explain 3 types of recovery methods. The end result of all 3 recovery methods is the same, that the orchestrator should be running again and blocks are created. It's important to note that all 3 recovery methods depend on proposals. Recoveries can only take place with the approval of the community, but it also means that all 3 recoveries rely on the NNS and therefore cannot be used to recover the NNS itself. My teammate Andrew talked about NNS recoveries in the past, last time at the Global R&D in November. The recovery is always coordinated by a recovery coordinator. This is usually a DFINITY employee, but it can be anybody. On the slide, you see the 3 recovery methods.
Yeah, because you're going to
Tracy differ. So the 3 recovery methods differ in their complexity and the amount of work that is needed. On the left, you see the simplest approach, which is an already existing one, and we can use it if the orchestrator is still running. In this case, a proposal can be created for adding SSH keys to the node. Then the recovery coordinator can SSH into the failing nodes and do the necessary work to restore the node to a working state. This recovery method already existed before SEV SMP. But when there is a more severe issue and the orchestrator cannot start, we have to use one of the new recovery methods, which I will explain now. In these cases, we need help from the node operators since the orchestrator is not running, so the registry changes are not synced to the node. Let's start with the simpler one, rolling back to the previous guest OS. Next slide, please. On the right, you can see that the host OS always contains 2 guest OS deployments. So when we do a guest OS upgrade, we don't overwrite the guest OS, but instead write a new version to the alternative guest OS deployment slot and boot into it. Therefore, the previous guest OS version is always available. And one of the main goals of SEV SMP protection is that only blessed guest OS versions can access the encrypted data on the node. However, we can always roll back to the previous guest OS version, which previously had access to the data. This does not have to go through the regular upgrade flow. So it works even if the guest OS doesn't boot up. We have an automatic mechanism which rolls back to the previous guest OS version when the new version does not properly boot. And in addition, a manual rollback is also available for node operators via the node console. The problem is that even after a rollback, once the old guest OS starts running, the orchestrator would attempt to upgrade to the broken version again because it sees that a new version is available, and then it tries to upgrade to it again, which is then rolled back again, creating this upgrade loop. So to avoid this, we introduced a way to recall a broken guest OS via the registry. Next slide, please. So these are the steps to roll back the guest OS. We first accept a set subnet operation level payload proposal, and we put the broken guest OS version into this record replica version IDs field. And with this, we can achieve that the guest OS no longer automatically upgrades. At this point, we can either automatically or manually roll back on the host. So we go back to the old guest OS version, which then has a working replica. But it could happen that a node is so severely broken that not even a rollback helps. For this worst case scenario, we created a mechanism which allows booting an alternative recovery guest OS, which has access to the encrypted data. Even in this case, the recovery guest OS is only allowed to run if it has been approved by the community. Next slide, please. So for this, the recovery coordinator prepares the code on a Git branch. This is a special recovery guest OS, which contains some code that is necessary to do the rollback. And once the code has been prepared, the node coordinator calculates the root file system hash. And this is a standard process. Every guest OS release has a root file system hash that is included in the blessing proposal. But for recoveries, we use a new proposal type, which is called the blessed alternative guest OS version. This contains the rootfs hash, the list of nodes where the recovery guest OS can run, and the base SEV launch measurement. And this is important because we want to limit on which nodes the recovery guest OS is allowed to run. And in addition, by publishing the rootfs hash, the community can verify the code that will run in this recovery guest OS, just like with regular guest OS releases. Once the proposal is accepted, the recovery image and the proposal, the accepted proposal, are distributed to the node operators, and they have to use the node console to boot up the recovery guest OS. During the boot of the recovery guest OS, it is checked that the proposal has been accepted and that all the fields in the proposal are correct. Once the verification has finished and everything is fine, the recovery guest OS boots up and the recovery can take place. I hope this short introduction gave you a good overview of the recovery processes under SEV SMP. But if you're interested in the technical details, please check out the Learning Hub article where you can learn a lot more. Thank you very much.
Thank you, David and Rudy, for this update on SEV Subnets. And I'm really looking forward to being able to run my first canisters on such a subnet. Really great. Thank you. Good. So, we conclude now on the feature section with additional options for critical proposals for SNS DAOs. And with that, I hand over to Jason.
Hi, everyone. My name is Jason from the governance team. And today I'd like to give a very quick update about a new SNS feature, which allows each SNS to have additional critical proposal types. To quickly recap what a critical proposal is, in the SNS, a normal proposal needs 50% of voting power among those that voted, and 3% of voting power among the total voting power, while a critical proposal needs 67% and 20%. Previously, the native proposal types, that is, those comes with the SNS framework instead of being defined by each SNS, they all have predetermined criticality. For example, transferring SNS treasury is always a critical proposal, while upgrading SNS controlled canister is a normal proposal. This new feature allows each SNS to specify more native critical proposal types. The main motivation behind this feature is that some SNS DApp canisters need to hold a significant amount of assets, and the normal voting threshold can pose a risk of rug pulling, where bad actors might aim to extract those assets under the DApp canister control with enough voting power. The way we implement this feature is through allowing additional critical proposal types to be specified either when creating an SNS using an NNS proposal or through an SNS proposal after the SNS is created. Next slide, please. Here are a little bit more details. For both NNS and the SNS proposals previously mentioned, an additional field is added as a list of IDs. For the SNS proposals, the existing action IDs and their default criticality can be found by calling the list topics endpoint on the SNS governance canister. When an SNS is launched, it usually requires an SNS init YAML file, and those IDs can be specified as human readable names in the YAML, just like other parameters in the file. It's also worth mentioning that if an SNS makes a normal proposal type critical, that particular action can still be reversed by passing another SNS proposal to remove the type from the list. But for the critical proposal types predetermined by the SNS framework, such as transferring SNS treasury, this feature does not allow them to become normal. On the right, you can find examples of configuring additional critical proposal types through either Candid or the SNS init YAML. As you can see, in both cases, the upgrade SNS controlled canister and the manage depth canister settings proposal types are added as critical proposals. That's everything from me. Thanks. And back to you, Bjorn.
Yeah, thank you, Jason. I think it's a very useful feature, in particular for DeFi focused SNSs. And yeah, thank you for sharing. Good. So with that, we can conclude the feature update section. And now we go to demos. And the first one is going to be on ckDOGE. I hand over to Mathieu. Please take it away.
Yeah, hi everyone. So my name is Mathieu. I'm part of the DeFi team here at DFINITY. And a couple of weeks ago, I announced that the Dogecoin integration was live on the internet computer, meaning that any canister can now interact with the Dogecoin blockchain and send transactions to it. And today I'm super happy to announce that the internet computer has a new chain key token, which is ckDOGE. And so what is ckDOGE? Well, it's an ICRC 1 and 2 compliant token. So it's can transact with it on ICRC 1 ledger on the internet computer. And the idea is that one ckDOGE is backed one-to-one with one Dogecoin. So why we developed this new token? Well, with the existing Dogecoin integration, canisters can already hold real Dogecoin. But now with the ckDOGE, we are making it super easy and super convenient for canisters to transact with Dogecoin. And in particular, canisters inherit all the nice benefits of transacting on ICRC1 ledger. So in terms of finality, transacting with the ckDOGE, so you have 1 second, around one in the order of 1 second for your transactions. Whereas transacting on Dogecoin, well, you have to have your transaction included into a block, which takes on average 1 minute. But then if you want to make sure that this block is actually part of the blockchain, then you want to wait for more blocks to be mined. So you may want to wait up until 60 minutes for your transactions. In terms of programmability, well, with the ckDOGE, you have all the nice smart contract features you have on the internet computer, such as HTTPS outcalls and timers. With Dogecoin, well, because Dogecoin is using the Bitcoin script, which is quite limiting, you have no support for smart contracts. And finally, for the fees, so ckDOGE transaction, they cost around 0.1 cent of USD per transaction. On Dogecoin, you will typically pay between 1 cent to 10 cents of USD per transaction. The central component of this token, apart from, of course, the ckDOGE ledger, is the ckDOGE minter, which is a canister whose role is to exchange Dogecoin on the Dogecoin blockchain for ckDOGE and make sure that this ckDOGE can then be redeemed for real Dogecoin on the Dogecoin blockchain. And so for this demo, I created a very simple app that will show you the two flows of the ckDOGE minter. So first the deposit flow, and then the withdraw flow. So the first thing we're going to do is to log in with our internet identity. So we'll get principal ID here. And as you can see, we can also check our balance. So it just got refreshed. And we already had some ckDOGE on our account. So 82 ckDOGE. But now let's say we would like to have more. So we'll contact the ckDOGE minter. And the first thing we're going to do is to get a deposit address, which will be associated with our account. So here is my deposit address. So I can now send some Dogecoin to this address. But then, unfortunately, I will have to wait for my transaction to be included into a block, and then blocks to be more blocks to be mined. So this might take around 60 minutes. So we won't have time to go through this full process. But what I did is to prepare actually a transaction in advance. So I deposited some Dogecoin. And this is the transaction that you can see here on this block explorer, Dogecoin block explorer. And you can see that this address corresponds to the deposit address I was given before. And I deposited 44 Dogecoin. And the important thing is that this transaction has more than 60 confirmation. So we can now go to the ckDOGE minter and call update balance, after which the ckDOGE minter will check the Dogecoin blockchain, see that there is a transaction that deposited some funds to that address, and mint ckDOGE on the corresponding amount on the ckDOGE ledger. And so as you can see, this is very fast. So we have now 44 ckDOGE on our account, and our ckDOGE balance just got updated. So this is all great. Now we can do all sorts of nice things with this ckDOGE. But now what I would like to show you is the second flow. So as I said, ckDOGE are backed one-to-one with Dogecoin. So at any point in time, we can redeem real Dogecoin out of this ckDOGE. And so this is what we're going to do now. So we will, so for this, we need a Dogecoin address that we control, to which the ckDOGE minter will withdraw the Dogecoin. So I have this address that I'm controlling. And there is a minimum withdrawal amount of 50 Doge. So we'll ask the ckDOGE minter to withdraw this amount. And so now the minter will create a Dogecoin transaction and burn our ckDOGE. And we have confirmation here. But of course, there are many things that are happening under the hood. And what I would like to show you now is actually we have a dashboard. Similarly, as for the ckBTC minter, which shows you the configuration for the ckDOGE minter, such as like the minimum retrieved Dogecoin amount of 50 Doge, the total amount of Dogecoin that are managed by the ckDOGE minter. And if we refresh that dashboard, yes, we should see our transaction here. So this is the withdrawal transaction that just got sent by the minter on the Dogecoin blockchain. And this is the address that I pasted, and this is the amount of 50 Doge that I was requesting. And if we click here, we'll see this transaction, which was caught up by this block explorer, but it hasn't been included in a block yet. We'd have to wait more time. But in the meantime, so let me go back to the slides and quickly explain to you how what was happening behind the scenes. So this is the flow, the first flow, so the deposit flow. So as a user, what I did was to request the deposit address from the ckDOGE minter, send some Dogecoin to that address, and then after 60 confirmation, so I notified the minter of the deposit using this update balance call. And finally, the ckDOGE minter was able to mint some ckDOGE on the ckDOGE ledger. And now conversely, for withdrawing, so what we did was to do an ICRC2 approve call on the ckDOGE ledger so that the ckDOGE minter could burn these ckDOGE and send the corresponding amount on the Dogecoin network minus the transaction fees, of course. So this flow is actually the same as for ckBTC. So if you're already familiar with ckBTC, you should be familiar with ckDOGE as well. But you can find here the documentation, the more precise documentation about this flow. And finally, we also have on dashboard.internetcomputer.org a dashboard showing all the transactions on the ckDOGE ledger. And yeah, last thing I wanted to say, so we are super excited with this new token, which concludes the Meridian milestone. And we're looking forward to seeing some cool dApps built on the IC that make holding and transacting with Dogecoin more fun and also more interesting. And if I have 1 second, let's see if my withdrawal was confirmed. Yes, got included into a block here. And yeah, we went full circle. So that's great. Thanks a lot for your attention. And yeah, back to you, Bjorn.
Yeah, thank you, Mathieu. So that's so summarizing, I understand like you are sort of 10 to 100 times faster and at the same time 10 to 100 times cheaper. So to me, that sounds like a pretty fair deal. So indeed, much wow. Thank you. Okay, let's go to the last demo of this Global R&D. I hand over to the Liquidium team. Please take it away.
Yeah, hi, I'm Robin from Liquidium, CEO and co-founder. Yeah, many of you who are in the Bitcoin community might have already heard about us from our previous product. We've been in the Bitcoin space for about 3 years now at this point, actively building. And basically what we've seen in the Bitcoin space is that there is a lot of people who have Bitcoin and they want to either earn yield on their Bitcoin or they want to put their Bitcoin to use by essentially being able to borrow against that. But the thing that they definitely don't want to do is sell their Bitcoin. And that's kind of like a pain point that we've seen. And obviously there are ways to borrow against Bitcoin already or put Bitcoin to work, but basically all of these solutions that are out there right now either need you to bridge to Ethereum or another chain, and usually these bridging solutions or wrapping solutions are custodial. For example, wrap.BTC might be the most famous one that's owned by BitGo. It's a custodial solution. And that kind of goes against the ethos of Bitcoin people. So Bitcoiners really want to use their Bitcoin and don't necessarily trust custodians. They want to have it decentralized and not having to trust anybody. And that's kind of the problem that we've obsessed about and tried to fix with Liquidium. So basically it's a cross-chain lending platform which allows you to supply Bitcoin, borrow stable coins against it on another chain, but then also going forward, we're adding more chains and more assets, allowing you to do all sorts of cross-chain lending activities. And yeah, today I just want to give you a quick demo of what that looks like. Let me just move around these Zoom windows here. So yeah, so first of all, I'm going to give you a quick overview of the UI, what it looks like here. So here right away, you can see a supply tab, a borrow tab, and a portfolio. So on the supply tab, you can see I have like a very simple input, almost like Uniswap style. We try to make it extremely user-friendly and as simple as possible. And then here you can select your asset. Right now we have Bitcoin and USDT. And then same thing on the borrow panel. But yeah, what I'm going to do now is I'm going to sign in with my wallet. So in this case, or I guess, yeah, I'm going to use Phantom because Phantom supports both native Bitcoin and Ethereum at the same time. So you can see here's my Phantom wallet. I have some Bitcoin in there. I do have some USDT in there. And then let me just connect that. And I'm going to connect it with Bitcoin. And then confirm here on the Bitcoin network. And then also I will connect my Ethereum wallet at the same time. So I'm just going to choose Phantom again. And what you can see now is I'm connected to my BC1Q address on the Bitcoin side. That's a native SegWit Bitcoin address. And then I'm also connected to the Ethereum address at the same time. And then what I can do is I can just supply some of my native Bitcoin here straight to the platform. So I don't have to go through any wrapping solutions or bridges. It's basically all in here. You just use native Bitcoin and I can supply that. So let me just do like whatever, 50%. And then for people that don't want to connect a Bitcoin wallet necessarily, like maybe people have a Bitcoin on a centralized exchange or on their ledger or something like that, and they don't want to deal with a Bitcoin hot wallet. They don't have to necessarily connect a Bitcoin address. They can just connect their Ethereum wallet. Or in the future, we're also working on internet identity integration and passkey so that you can just not use a wallet at all and just create an account here. And then essentially what you can do is you can just use a deposit address to supply. So if I do that, then I get a Bitcoin address that I can send Bitcoin to, and then it gets supplied to my Liquidium account. But in this case, because I have a Bitcoin wallet and Ethereum wallet, I'm just going to choose wallet. And then I will hit supply here. And you can see the Phantom wallet popping up, and it asks me to supply that amount on Bitcoin mainnet on the Bitcoin network. Now hit confirm. And then that approves, submitting the deposit. And then this just takes a second. And then here we can see it was a success. Now the Bitcoin is basically being supplied to Liquidium. This takes around 40 minutes. So that's 4 blocks. Because what's happening in the background is that I'm basically sending in native Bitcoin. And in the background, this is being converted into ckBTC. So 4 blocks is what the ckBTC minter needs in order to confirm the Bitcoin transaction and mint the ckBTC on the other side. And then that ckBTC essentially gets attributed to my Liquidium account. And because we don't want to wait 40 minutes now, I've already prepared and supplied some BTC beforehand. And yeah, here you can see I already have like a supplied BTC position. And essentially when I'm supplying Bitcoin, 2 things happen with that Bitcoin. First of all, I'm earning yield on that Bitcoin because similar to other DeFi lending platforms, when I'm supplying the Bitcoin or when I'm depositing the Bitcoin, then it gets available for other people to borrow in the background. So it gets added to a liquidity pool that other people can borrow from. And these people pay interest, and therefore this interest is basically forwarded to me. So I'm earning interest on my Bitcoin, and at the same time, it also becomes available as collateral, which means I can now borrow against that Bitcoin as well. And you can see I already have a borrow position, but I'm just going to create a new borrow position here. So I'm heading to the borrow tab, and then I want to borrow some USDT against it. Why would I borrow USDT against BTC? I think that answer is pretty clear. I don't want to sell my Bitcoin. I want to keep my Bitcoin and still have liquidity available for any sort of use case. So that's really more like this is what is about here. And then I can just, for example, borrow 50 USDT. And then I can click borrow here. And now it asks me to confirm on the Bitcoin network again. This is just basically a wallet signature to tell the my ICP account, like, hey, yep, verify that, release the BTC, the USDT to the user. And then you can see success here. USDT was initiated, and borrowing only takes around, so we're overestimating here, it only takes around 1 minute or so, because essentially just USDT is being sent to your address. What I did now for borrowing is I borrowed straight to my connected wallet, which means once this transaction is done, once it was broadcasted, the USDT will arrive directly into my Phantom wallet. If I don't want to borrow to my connected wallet, or if I don't even have a wallet connected, what I can do instead is I can also use a borrow address, which means then I can just borrow, put in an Ethereum address. For example, if I want to send that USDT to my centralized exchange or to my ledger or whatever it might be, I can just put that Ethereum address in there, and then it lands there instead of my wallet. So these are kind of the main functions, supply and borrow. I also have my portfolio here. I already showed that briefly. So I can see my supply positions. I can see my borrow positions. And then I can also see my portfolio health at the top. So that is basically just a value. So right now I'm going from 25% to 27.6% because I've supplied more Bitcoin. So the higher the portfolio health, the better. If I ever reach 0% portfolio health, that's when I run the risk of being liquidated. And the portfolio health is basically a factor of how much did I supply, how much did I borrow. And if, for example, now Bitcoin would plummet in price, then obviously the dollar value of my Bitcoin that is supplied goes down. Therefore, my portfolio health goes down, and I run the risk of being liquidated if it reaches a certain threshold here. In order to prevent liquidations, we do have a very solid notification system in place. So if you click here on the notifications, I can connect my email address, I can connect my Telegram, and then basically as soon as you hit various portfolio health thresholds, you'll get a message warning you to then repay your position partially or supply some more collateral. That's also possible here in the portfolio. You have supply more, you can withdraw your Bitcoin at any point in time, and then also you can repay your borrowed amount or borrow more at any point in time. This is basically the main thing. Incredibly simple. User experience was definitely one of the most important things here. And then for power users that want to see some more data and details, there is a markets tab where you can see the market. So we can see, for example, here the Bitcoin market. We can see the interest model, the different various interest rates at various utilization rates, optimal rate, and so on. And same for USDT. And so that's basically where, if you want to have the pro tools, you have them accessible. But for the average user, I would say just stay here in the home tab, and it's super simple. And in terms of the architecture, as I've already mentioned, in the background, this is using an ICP canister and using chain key signatures to basically handle the facilitation of the assets in the background by holding CK assets on the protocol. Using CK assets in the protocol also allows for super quick liquidations. Liquidations are kind of like the most important thing for a lending platform because you don't want to accumulate bad debt. And by using CK assets, we can do liquidations in seconds. I think that covers pretty much everything here. We are working, just because this is obviously an ICP community call. Right now, OISI wallet only supports Ethereum connection directly. We're working with the team to also get a Bitcoin connection in place. So then you should also be able to use OISI wallet extremely smoothly. But right now you can already use OISI wallet by just connecting it to Ethereum and then depositing to that deposit address here. But yeah, I think that covers pretty much everything. We're working on adding more chains and more assets. If you have any feedback, any requests for new assets and new chains, such as Doge, for example, then happy to get that feedback and see if we can squeeze it into the timeline. You can find our landing page at liquidium.fi, so you can learn more there. There's also docs, and then the application itself is on app.liquidium.fi. Thanks for having me.
Thank you very much. We like, I mean, it's a really cool use case, making full use of ICP cross-chain technology. So yeah, it's very impressive. And I also really like your app. I mean, very smooth. It seems very easy to use. So congrats for that. I hope you have enjoyed it as much as I did. And I wish you a great day and talk to you soon.